Hello everyone, today we're talking about coordinate systems. This is material from 4.4. So we'll kind of see today how these bases are important for us. So let me recall something from last time, from last lecture, that suppose B, let's say, is B1 through BP is a basis for, let's say, a vector space V, and X is any vector in V, then there exist these weights, unique weights, let's call them C1 through CP, such that I can write that vector X as a linear combination of the B's with those weights. So B1, then C2, B2. All right, so we proved this last time that we knew that there was going to be some way to write the vector X as a linear combination because this is a spanning set, right? When you have a basis, that's always a spanning set. And then the fact that it's a linearly independent set implies that this is a unique way to write it. Okay, so this leads to a definition. Well, remember, you gave me this vector X, and it comes with these weights. So what I'm going to say is that the weights C1 through CP are called the B coordinates of X. Coordinates of the vector X. Okay? And this is denoted, let's see, so his notation is X with the subscript B. And I'm going to write this as, the weights are a bunch of numbers. I'm going to put them into a vector. This is a vector in RP. Okay, so one more time. You fix the basis for the vector space V, and then you gave me a vector X. Well, that tells me that I can write the vector X in a unique way as a linear combination of those elements in the basis, and those weights are called the B coordinates. And I'm going to put those weights into a vector, and why do I do that? Well, notice then this transformation then, I get a transformation that eats vectors in V and spits them out in RP, and it's given by, well, I'll take a vector X, right? The vector X was a vector in V, and then it spits out a vector in RP. This is called the coordinate mapping. Okay? And what's kind of nice about this that we'll come back to in a second is that this vector space V could be any kind of abstract vector space like polynomials or matrices or any other kind of abstract vector space. But it gives you a representation, they call it, right, in RP. Okay, so let's do an example. I think this will make more sense. We see a little example. So something you might see on your homework is the following. E.g., let's consider this basis. So 1, 0, 1, 2. Let's suppose that this is a basis. Well, we know this is a basis for R2. How did I know this was a basis for R2? Well, remember, if I want a basis for Rn, I want to look at, this matrix I get by putting these in the columns, and this is invertible, and you can see that it has two pivots, and therefore the columns form a basis for R2. Okay, now let X be, I don't know, let's take it to be, did I write down an example? Let's take X to be 4, 3, and I want you to find the coordinate, the B coordinates, right? The B coordinates of this vector with respect to this basis here, okay? So what we're doing here, I think you can draw a little picture. So the idea is that we've got R2, okay? And you've given me these two basis vectors, 1, 0, which is something like this, right? So let's call that like B1. And then B2 was this vector 1, 2, so that was something like this. And then you said, okay, then let's take this third vector, right? So that's a basis. And now we said, okay, give me this vector X, which is, let's see, 1, 2, 3, 4, right? Something like 4, 3, so something like this. This is the vector X. And I want to write this vector as a linear combination of b1 and b2. Okay, and that's what that's saying. It's saying, how do I do that? What are the coordinates? Okay, so in other words, yeah, we know we can do it in a unique way, and I want to know what is that way, right? So we want to write the vector x for 3 as something times the first vector plus something times the second vector, right? And those numbers, the weights, will be the coordinate, the b coordinates. Okay, so what is this? Well, notice that this is something familiar, right? What is this? This is nothing but a vector equation, because I have a vector that I want to write as a linear combination with unknown weights. That's exactly what a vector equation is. And that's good news because we know how to solve such a thing. So we solve the underlying system of linear equations. So remember, you take those vectors as the coefficient matrix and you augment with the thing you're shooting for. And then we want to solve this thing, so we know it's consistent. We want to know what the solution is. Let me put this into reduced row echelon. So I scale that last row, and then I'll clear above this pivot, above the pivot. So this is going to be 0, 1, 3 halves. I'm going to take minus 1 of that row, add it to the first row. So this is minus 3 halves plus 8 halves. This is 5 halves, right? So what this is telling me is that the b coordinates of x are 5 halves, 3 halves. And you can actually check this, right? So this is typical that if you have a proposed or a solution that you think works, you can actually check that what happens when I take 5 halves times 1, 0 plus 3 halves times 1, 2. Indeed, I get, let's see, so 5 halves plus 3 halves is 4, 8 halves, and then this is 3. So yeah, I get what I'm shooting for. So let me try to draw, hopefully this doesn't get too messy, but let me try to draw the picture. So it's saying that I take 5 halves of this. So 5 halves of vector 1, which was something like this, right? That's like 5 halves b1. And then I want to take 3 halves of b2. So 3 halves is like 1.5, so this is something like that. And then, yeah, that's not too bad, right? When I add those together, I get the x that I was shooting for. Okay. Okay, so that's the idea behind b coordinates. Let me actually talk about how you kind of use these. So how to use these kind of b coordinates. And again, the main application, or at least one of the applications, will be to the context of abstract vector spaces. So let me just do this with an example. So let's consider the space P2. Remember, P2 was the polynomials of degree at most 2, right? And now this has a basis. P2 has a basis given by, so these will be polynomials. I claim 1t and t squared, right? So, I mean, why is this a basis? Because, of course, if I take any polynomial, right, of degree at most 2, I can write that as something times 1 plus something times t plus something times t squared. It's almost a tautology that this is a basis, right? Because the way you think about a polynomial is it's something times 1, some constant term, plus something times t, the linear term, and then the quadratic. So this is a basis. So note actually that what's the dimension of P2? P2 actually has dimension 3, because there's 3 elements in a basis. And now what I want you to do is to consider the set let's say 1 plus t squared is my first element, 4 plus t plus 5t squared is my second element, and then let's take 3 plus 2t. So this is a collection of vectors, if you like, right? This is kind of like v1, v2, v3. These are vectors in the space of polynomials. And I want to know, is this set linearly independent? Okay, so, this is kind of weird because now we don't have vectors in R whatever to deal with. We can't just make a matrix out of them, okay? So what we're going to do is we're going to think about, these b coordinates and represent them as vectors in R3. So the idea is find the B coordinates for each vector, and, represent them, use this to represent them as vectors in R3. Okay, so what do I mean by that? Well, notice that V1, right? So, for instance, V1, how do I write that in terms of the basis? So remember the basis up here, well, let's see. So V1 is equal to 1 plus 0t plus 2t squared. So what that's saying is that the B coordinates of this guy are just, well, those numbers, right? So this is kind of, again, so natural that you're not even used to doing it maybe, but 1, 0, 2 are the B coordinates of this thing. Okay? And similarly, I think you can see that V2 is, well, since V2 is 4 plus t plus 5t squared, this implies that the B coordinates of V2 are going to be, what is that, 4, 1, 5. And of course, that's the B coordinates. The B coordinates of V3 would be just the entries of here, so it's 3 plus 2t plus 0t squared. And then the idea now is, right, we have these B coordinates, okay, and we can represent them as vectors in R3 now. Okay, so let me just draw kind of my usual cartoon of what's going on here. Is that, right, we started with this world P3, or sorry, P2, right, the polynomials of degree at most 2. We had 3 polynomials. We had V1, V2, V3. And when we took these coordinates, and then we fixed the basis, I should say, there was a basis that we fixed that was 1t squared. Okay, so we had this polynomials, we had these 3 vectors that we are considering. And once we fix this basis, we can then take the coordinate vectors to actually represent each vector as, something in R3 now. So like V1 got sent to, see if you can see it here, V1 got sent to 1, 0, 2. Right, V2 got sent to 4, 1, 5. V3 got sent to 3, 3, 2, 0. So maybe I'll just try to use this color maybe. So I'm not going to worry about coordinates, but this was V1, B, the coordinate vector for B, and this was V2, the B coordinates for V2, and then V3 was something over here. Okay, so hopefully this is making some sense that I'm taking vectors in this P2. With respect to this basis, it gives me vectors in R3, and just the fact that I'm using that, I'm going to mostly rely on the book to justify here, is that this transformation that eats vectors in P2 and spits it out in R3 is linear and is one-to-one and onto. Okay, so this is a transformation, right? It's eating vectors in P2, spitting them out in P3, in R3, right? It's one-to-one and onto, and this is called what's called an isomorphism of vector spaces. But the point of all of this is that if I'm asking a question about linear independence of these 3 vectors, I can ask the same question in R3. So this preserves notions of linear independence, etc. Okay, so we're getting pretty abstract here. Let me just go, the whole point of this is that we take the abstract world into this R3. So let me go back to the question here. You gave me these 3 vectors in P2, and I want to know, are they linearly independent, right? So here's how I'm doing this. I'm taking the coordinate vectors of each of the 3 polynomials you gave me. Okay, and what I'm going to do now is here we just consider the set of those coordinate vectors. So the B coordinate vectors, which were 1, 0, 2, 4, 1, 5, 3, 2, 0. Okay? And so the linear independence or dependence of these 3 vectors is translated into the same question, but here this is now in R3, which we know and love because we know how to deal with vectors in R3. We just look at matrices, right? So here we consider the matrix 1, 0, 2, 4, 1, 5, 3, 2, 0. You know, and to do the usual thing, row reduce, I think I'll spare you the details, but it looks like something like this in the echelon form. It turns out you only have pivots in column 1, column 2. So what do you know? What do you see here? You're missing a pivot, so this implies that the set is actually linearly dependent. Okay? Okay, so after all that, you know, again, the whole point of this idea is that we took these polynomials that were, you know, these vectors that were in this abstract vector space, translate them into the world of Rn, in this case R3, and then just do your usual thing, get your answer. Okay, so that's it for today. We'll continue next time.